Hi, everyone. Thank you for joining me today. My name is Andy Jaros, and I'm with Logix Technologies, Inc. Today, I'm going to talk a little bit about embedded FPGA and evaluating embedded FPGA. We're starting to see a lot of demand for this type of IP coming from our customers and being requested from our Asic design partners from their customers. So the adoption is really taking off. The question is it time to get on board? And so that's what we're going to talk about today. And so the most obvious question you would ask, or at least I would ask being the sales guys for embedded FPGA IP, is why wouldn't you use it? You get the FPGA functionality inside of an ASIC. You get that flexibility that you can change circuitries post-silicon and after you've taped out. You can support any kind of hardware acceleration that an end customer might require. And you can also have customizable solutions for different customers, different applications, all with a single chip tape out. So it does have a lot of true benefits for both the semiconductor company as well as systems companies. And the other thing you can add support is better security. So embedded FPGA allows you to obfuscate circuitry that maybe you have a proprietary customer that has proprietary circuits that they want put in that they don't want to share with the semiconductor manufacturer or the foundry, or even if you have export control issues where certain regions that you want to sell your chip into restrict your chip because of the algorithms that are embedded in silicon. Well, using embedded FPGA, you can actually program those security algorithms or encryption algorithms after the chip has already been in the region, and thereby kind of avoid or get around some of the export control regulations. And you can set that up so that you have one chip that can support multiple different regions. So there's a lot of use cases for embedded FPGA that makes a lot of sense. From a system standpoint, we're seeing areas where customers want to integrate their FPGA that's sitting next to their applications processor. That allows them to reduce system costs. It also allows them to get better system performance because basically they're reducing the amount of data and transfer between going from the applications processor or main chip to the FPGA and back. So you don't have to worry about signal integrity or anything like that when it's all on the same chip. And it also improves power. You're actually reducing some of the redundancy associated with some of the peripherals that are both on the applications chip as well as the FPGA, such as SerDes, PHYs, GPOs. And all that means is just you're shrinking the area at the system level, which obviously lowers power and lowers system cost. So, we've all have been told by salespeople and marketing people about the latest and greatest technology and that you should go and evaluate it. But the truth is, evaluations take time, they take resources, they take away from the core development of some of your engineering team. And it can be very complicated, as shown by the chart on the right. And, I've been through a lot of evaluations with customers here at Logix, and basically we get a myriad of results from an evaluation. The best result is usually, when the evaluation provides results that are exactly as expected or what we're hoped for. Many times we kind of get okay results, and those okay results are, the customer has gotten very familiar with our technology. They understand how it works a little bit more, what the pitfalls are, what the positives are, and maybe it wasn't a good fit for the initial project that kicked off the evaluation. But now they understand how this technology and how this IP works, and now they're starting to think about future projects where it could come into play. And then there are those that are kind of bad results, where the results don't live up to the salesperson's hype, and the customer walks away thinking that was a complete waste of time. And so what this presentation is supposed to do is really kind of targeted at learning and understanding what are some of the pitfalls, so you have the right expectations when you go into evaluating embedded FPGA IP. So hopefully we get good results at the very end. So we'll be taking a look at using embedded FPGA from two different perspectives. One is from the ASIC designer considering adding embedded FPGA to their chip. And then we're also going to take a look at it from the perspective of people who have been using FPGAs in products and their volumes are getting to a high enough level that they want to do an ASIC, but they want to retain some of that FPGA functionality and reconfigurability in that ASIC. So if you're coming from an ASIC, kind of what we've seen happen the majority of the time is, ASIC designers, they've been in the ASIC design flow and they may not fully understand or appreciate the differences within an FPGA. I mean, there are differences in the technology, as everybody knows. But until you kind of get in and start working with both technologies, you don't really understand the subtlety differences between the two. With usually a semiconductor company, the first thing that happens is they'll take a known design that they've used in an ASIC, maybe for generations, and it's very logical to go do that because it's has a known functionality, has known performance in a known area, and then they'll take that design, put it in an FPGA, run it through the software tools, and surprise, surprise, it takes up more area, is slower, and probably takes more power. So, if you look at a comparison of an ASIC design and compare it with your ASIC results and your FPGA results, the results are going to be disappointing every time. The ASIC is going to win. Now, you can dive deeper into kind of why that is. The pitfalls in doing that type of an evaluation is there's basically a couple of different major differences, but they're actually fairly subtle. One is coding style. So in the coding style is very different for ASIC versus FPGA. So for example, in that ASIC design flow, use of latches is fine, but they're not very well supported in FPGA, and they can provide very unpredictable results. Conversely, a lot of ASIC designs try to stay away from using flip-flops because they do consume area, make the design a little bit more complicated. But with FPGA, we encourage people to take advantage of the flip-flops because they're already in the fabric, they're already built into the reconfigurability circuitry, so they're basically for free. So really, you should not shy away from that. And there are other differences in coding style, and we kind of have a guide in an app note that can help walk you through that. The other thing that we see is that ASIC designs tend to be over-provisioned. And what I mean by that is you might have a controller or state machine on steroids. Maybe it's a bring-up state machine for different IP islands in your ASIC. Every customer may want to bring those up differently or in a different sequence, or an interrupt controller for that matter, where the designer is really trying to anticipate every potential use case that a myriad of customers could have for their particular chip. And when you look at using an FPGA fabric for that functionality, now you kind of have to shift your thinking in that you don't really need that over-provisioned design, because you can reprogram that FPGA anytime for any reason very easily. So now all of a sudden that big over-provisioned complex controller can be a very simple controller geared at particular applications or customer requirements. So that one single complicated controller gets replaced by a library of much more simple controllers that can be reprogrammed and modified and edited for any future customer. So that's kind of where you think, when you think about what you want to use for an evaluation, you really got to think about what parts and what really needs configurability. The other thing that really most people should be aware of, and I think everybody knows that embedded FPGA area is going to be larger for the same circuitry versus ASIC. People throw out 10 LUTs to 10 ASIC gates to 1 LUT kind of as a ratio, and that's kind of a good ballpark. But that doesn't tell you anything about how much area is going to be, and there's a lot of applications that are very area sensitive. So the area implication can actually be quite extensive. It can be anywhere from 30 to 70 times bigger than an ASIC, meaning that the same design in an embedded FPGA could be that much larger than in ASIC gates. And so that's where you kind of want to think about, what parts of your design you really want to put into FPGA versus ASIC gates, and start thinking about partitioning, because you really do kind of want to minimize the amount of configurability that you put on chip, so you don't have a big area blow. And the other thing that you really should be thinking about in terms of where to put embedded FPGA is think about your system, your chip architecture, and think about where you need programmability. There are a number of different ways that you can provide programmability, whether it's a CPU, a DSP, a GPU, a sophisticated state machine like we mentioned earlier, or you can use embedded FPGA. And each one is going to have their benefits in pros and cons. From an embedded FPGA, you get near ASIC type performance. With ASIC gates, you get full programmability, and you can support DSP functions and very wide data buses and wide data transactions very easily, much more easily than a CPU, DSP, or GPU. So that's where embedded FPGA kind of comes into play. It does a lot of things very well, and particularly when all the market hype is about accelerators, working on big data sets or wide data. Embedded FPGA really has a play for supporting those type of programmable requirements. So that kind of covers kind of the highlights of what to watch out for if you're coming from an ASIC. Now, if you're coming from an FPGA, you would think that if you got a design running in FPGA, it will run pretty much the same in embedded FPGA, and you'd be mostly correct. The functionality is the same, the structures are pretty much the same, so there really is not that much of a difference between the two. But what you do need to be aware of that is not all FPGA primitives that you might be using with your Xilinx or Intel part may be supported with the embedded FPGA. So for example, there's a buffer IO, PLL, gigabit transceiver buffers. Those are all primitives that are supported in Xilinx Vivado, and those are needed at the FPGA chip level. But when you have an integrated IP, you don't necessarily need that support because the signals aren't necessarily talking to those hardware resources that are on chip from the IP perspective. The other big thing that I think is kind of a surprise is that if you have a design running in say a Xilinx FPGA at 28 nanometer, you'd get the similar performance on the embedded IP running at 28 nanometer. And that is actually not quite true. And the reason for that is FPGA companies, they tend to have a specialized process. So it's a more performance-tuned process, and it's different than what's available for the standard ASIC and COT flows that are offered by the foundries. So you've got kind of a difference in process rules and target requirements for those different process rules. The other thing that FPGA companies do is they speed bin their parts. So if you're using a very the fastest speed bin, it's going to be very difficult for an embedded FPGA in the same process node to be able to hit that same performance point. And then the other main thing is FPGAs support run at a higher supply voltage than the standard foundry process. So if you got a design that you're running in an FPGA and you're looking to stay in the same process node, it will run slower in that process node. In our rule of thumb that we tell customers is that if you kind of take your design, run it in a Xilinx -1 speed grade, that's roughly equivalent to about the typical corner in the same process node. And, as you know, as you're doing an ASIC, you want to be able to use 100% of the distribution. So you may end up having to either speed bin your parts, you may want to run at a higher threshold voltage, or drop down one process node when you're considering doing an ASIC if you have a particular performance requirement that you need that you're getting out of an existing FPGA. So those are kind of the gotchas, or the things that I shouldn't say gotchas, but really things to be aware about when you're starting off an embedded FPGA evaluation. Because if you have the kind of the right set of expectations of what the IP can and can't do, then you can save yourself a lot of time and possibly frustration before you actually start an evaluation. In terms of our availability with FlexLogix, we support all the most popular process nodes. You can see that we've got some new processes that we're bringing online this year, being TSMC 7 and GlobalFoundries 22 are the latest. It takes us about 6 to 8 months to port to a new process node. And we can build any size array once the technology is already ported in a matter of days to a week or two. So we can support any size embedded FPGA, any combination of logic and DSP requirements that are needed, including VRAM, very easily once the process has been supported. So, as kind of wrapping up the presentation, we are seeing strong traction with embedded FPGA in a wide variety of markets. It's being requested in wireless 5G applications, smart NICs, smart NIC switches, storage, microcontrollers, and IoT end devices, as well as aerospace. So, it is a great time to start looking at embedded FPGA to see how it can enhance your chip's flexibility and broader appeal, extend life cycles at the system level, be able to do in-system upgrades. It really is a good time to be able to look at embedded FPGA. And hopefully I've kind of given you some background and foundation so that when you start the evaluation, it gives you a really good reference of what to expect so that you do have those very positive and great results at the end of the evaluation. And with that, we would love to help navigate you on this journey, kicking off an evaluation and kind of talking through from an architectural standpoint where it makes sense and where it might not make sense. And so we invite you to reach out to us and learn more about how embedded FPGA can help you. Thank you.